Hello students, I am going to explain about electric dipole. That electric dipole dipole concept involves or includes the ideas about dipole moment. Dipole moment. Okay, let us first understand what is the meaning of movement. Movement. Concept of movement. Actually, the concept of movement is said to be introduced by Archimedes. Archimedes of 287 to 212 BC. Okay, anyway, he was the person belonging to third century BC. Third century BC. He was a mathematician, physicist. He introduced the concept of movement. Okay, he introduced the concept of movement while discussing or while explaining balancing of levers. Balancing of levers. Okay, an example of lever is shown. This is horizontal beam. A horizontal beam is taken. On this beam, you are seeing at one edge there is a mass m1, very small mass m1 compared to mass m2, which is at other end. Anyway, this beam is balanced. This fulcrum means support. Fulcrum means a support is placed very closer to mass m2. Okay, even though mass m1 is smaller than mass m2, mass m1 is balancing m2 because it is placed at a distance far away from the fulcrum. Far away from the fulcrum. The distance is measured to be d1 meters, and the distance d2 is to be in meters, and the d2 is the distance from fulcrum support to m2, and d1 is the distance from support point to m1. Okay, in other words, a smaller mass will balance larger mass. A smaller mass will balance larger mass provided if it is placed at far away distance from the supporting point. That is what the principle discovered by Archimedes. Archimedes. In other words, the smaller mass is equal to larger mass. A smaller mass is equal to is effective as a larger mass provided if it is placed at far away distance from the support. Such kind of levers were used in 500 years back, 5000 years back. 5000 years back, I will show you the levers. For example, you see this. There are some examples are there here. This is the lever in use 5000 years back. See that here very large weight is there, very large mass is there, but here very small mass is there, and that small mass is used, and the small mass is effectively acting as large mass, and so for this particular person to lift this small mass very easily, okay, this counterweight to balance this lever. This counterweight will pull this bucket of water up, and this counterweight is doing work using lever principle. Okay, this is what happened 5000 years back in Mesopotamia. And there are some more images, the same kind of image, and especially these lever mechanisms were in use to lift the water from the well, very easily. That is what there. And next, here also the same mechanism is. So in other words, very in ancient world, levers were used to lift the water from the deep in the well. Okay. So the Archimedes was just 200 BC, but we are talking about 3000 BC. 3000 BC. That is what Archimedes belonging to only just 200 BC. 5000 years back means 3000 years back, 3000 BC means. Okay. And Archimedes finally concluded this equation: m1 d1 is equal to m2 d2. m1 d1 is equal to m2 d2. Okay, I will show you this. M1 d1 is equal to m2 d2. Okay. All right, just wait. This is what m1 d1 is equal to m2 d2. This is the formula invented by our Archimedes. m1 d1 is equal to m2 d2. Okay, let us move to another slide. And suppose if you multiply m1 by g, small g, on both sides, left hand side and right hand side, what you will find is m1 into g is gravitational force. Therefore, you are expressing Archimedes principle in terms of gravitational force like this: m1 f1g d1 f2g d2. And we are calling gravitational force as weight. Therefore, w1 d1 is equal to w2 d2. This is what we are using at the present day. Anyway, in this formula you are finding weight and distance. That is important. See that in this formula you are finding weight and distance, or force into distance. That force into distance later is becoming moment. Okay. Weight into distance. The study of mechanics was intensified in 1500 AD. So scientists of that period introduced the word momentum for body moving in straight line. If a body is moving in straight line, they called momentum as mass into velocity. The word moment is used for the case where body is going to rotate to mean force into distance. Okay, the two words are introduced by scientists who were studying mechanics. One is momentum, another one is movement. Movement is used whenever force is causing rotation. And movement formula is force into distance. Just now we verified that Archimedes principle also converted into force into distance formula. Actually, Archimedes had given m1 into d1 equal m2 into d2. The modern scientists, what they did, they multiplied g on both sides. So it becomes m1 into g d1, m2 into g d2. But m1 into g is equal to the weight into d1, weight into d2. So weight is a gravitational force. Force into distance is movement. That is what the later scientists introduced. So anyway, when mechanics was going to be studied very seriously in 1500 ADs, the scientists introduced two concepts. One is momentum, another one is movement. Momentum is the mass into velocity. That concept is attached to the case where body is moving along a straight line. The concept called movement is used where a force is causing rotation in the body. Then the concept called moment is equal to force into distance is introduced, and that force is nothing but gravitational force. That gravitational force is also called weight. Weight into distance is entered into the science of mechanics. Okay, why we use the terms moment and torque? Okay, there are also actually another word is there, torque. Torque also related to rotational mechanics. Moment is related to rotational mechanics. Why we are introducing two terms like moment and torque, even though formulas of torque and moment are same? Remember that. The formula for moment is defined as m bar is equal to r bar cross f bar. The torque is also defined as r bar cross f bar. Then why we are introducing two concepts, say moment and torque, in the rotational mechanics? If the formulas are same, then why we are using two different terms? The reason is movement is used to indicate the situation where applied force is not causing rotation but making the object to oppose the rotation. Moment is used to indicate the situation where applied force is not causing rotation but making the object to oppose the rotation. To understand this, you have to consider one particular case. Let us go to a next slide. Okay, here a swimming pool is shown, a skating board is shown above there, and when you see, if you have seen Olympics, divers will stand at this edge of the skating board. From this edge they will jump into the swimming pool. Okay, and that is a competition, very tough competition in the Olympic Games. Okay, many medals were won by America and China in this competition. Okay, anyway, and see that when a diver, when diver is present at the edge of the skating board like this in figure B, what is happening? The skating board is bending. That skating board is bending as if it is going to rotate, but it is not rotating. But it is not rotating. What is happening? Once the diver jumps into the swimming pool, the skating board will come back to its initial position. The skating board will come back to initial position like this. So anyway, here the force is causing the skating board to rotate, but it is not rotating. Because the skating board will come back to its initial position once the diver jumped into the swimming pool. In such cases, we use the word movement. Okay. Here diver is applying downward force on the skating board's edge, but board is bending but not rotating. Usually, if you apply force on the edge, the body should rotate. Actually, if you apply some force on the pen edge, suppose if there is a pen on the table, and if you apply force at the edge of the pen will rotate. But here, even though you are applying a gravitational force at the edge of the skating board, gravitational force means mass into g. When a person stands at the edge, he is applying gravitational force, downward gravitational force m into g. That downward gravitational force is applied at the edge. Then this skating board should rotate, but it is not rotating because other end is fixed to some support. Okay, that is the reason. So anyway, once the diver jumps into the board, the skating board will come back to its initial position. In such cases, we use movement. Now coming to this second case, here a fixed axis is there about which a door is rotating. Suppose if you apply a force at the edge of the door will rotate, and rotate means it will move from A to B along a arc path, along a circular path. Once the door reaches point B, it will not come back to A. Unless some force is applied. Therefore, here a rotation is happening. In such cases, we use the concept called torque. Torque is equal to distance cross product of F bar, R bar cross F bar. Okay, and movement formula is R bar plus F bar. And movement concept we use where object is tending to rotate but not rotate, or it will oppose the rotation. And torque is a concept that we use where force is actually causing rotation. Okay. These are the points you see. Electric dipole. What is electric dipole? Okay, let us come back to electric dipole, because electric dipole also involves a concept called electric dipole moment. And hence I have introduced the concept of moment just before the discussion of electric dipole. Electric dipole means the positive and negative charges are separated by some distance d meters. Okay, it is surprised how it is possible for positive and negative charges to be separated by some fixed distance, because there is attractive force between positive and negative charges, and so they will no longer be separated by fixed distance by themselves unless some external forces act. Okay, but if you see the chemical compounds like NaCl, sodium chloride, the sodium chloride is formed because of the positive ion of Na plus and negative ion of Cl minus. This positive, there is attractive force between sodium positive ion and chlorine negative ion. Because of this attraction force, Na plus and Cl minus come close together. But when they come very close, what will happen is the innermost electrons of sodium and chlorine will apply repulsive force, and so Na plus and Cl minus again will move away. Once they move away, again attractive force will become dominant, and so they will come very close. Once they come very close, the repulsive force become dominant, and because of internal electrons of the Na plus and Cl minus. Okay, anyway, at some point, both attractive and repulsive forces will balance. At that distance, Na plus and Cl minus remain. Okay, Na plus and Cl minus will stand with some particular fixed distance between them. On average basis, there is a fixed distance between them, Na plus and Cl minus. That is called bond length. Bond length. Okay. That is why it is possible for dipole to exist. In the dipole, you will find a positive and negative charges separated by fixed distance. See, here I have shown electric field of dipole. Here electric field is shown not by vectors, by electric lines. Electric lines of force are assumed to start from positive charge and will end on negative charge. Okay, why they start from positive charge and will end on negative charge? All those things are explained while explaining electric field and electric line of force. That is why I am not explaining here those points. If you want, you can refer my previous class where I discussed about electric field and electric lines of force. Anyway, in the dipole electric field, electric lines will start from positive charge and will end on negative charge. And remember that at point A, that is exactly at the middle of the middle plane of the positive and negative charges, the electric field is horizontal from left to right. Again, at positive charge, perpendicular to positive charge, there is a line going along a straight line towards left. Again, for the negative charge, you will find another line exactly along horizontal line towards negative charge. Now, let us come to the case of point A. See, point A is shown here now. A point A is shown. If you draw a middle plane here, like this, middle plane here, the point A will lie or will become one of the point of middle plane. I am considering that point here. I am considering this point A, which is lying on the middle plane of the positive charge and negative charge in the next figure. See that this is the figure. This is the figure. Here a positive charge is there, a negative charge is there, and if there is a middle plane, that middle plane will be like this. Middle plane will be like this. On this middle plane, I have identified a point A. Point A. At point A, the positive charge is producing electric field along the line joining the 2 points. See that at A, the electric field of Q plus is EQ plus like this. Similarly, at point A, negative charge also produce electric field EQ minus along the line joining the 2 points like this. I told you electric field for negative charge is towards negative charge. Electric field for positive charge is away from the positive charge. Therefore, EQ plus and EQ minus directions are as shown in this figure. Now, we are separating this EQ plus and EQ minus as horizontal and vertical components. How? By drawing imaginary x-axis like this, by drawing imaginary y-axis like this. See that. Here imaginary y-axis is drawn like this, imaginary x-axis is drawn here. Then EQ plus can be separated into EQ x component, EQ plus y component. Similarly, EQ negative is separated into EQ negative x component, EQ negative y component. But EQ y plus component and EQ minus y component are opposite and are equal. Therefore, y components will cancel, but x components will not cancel because they are in the same direction. Same direction of x positive x-axis. Therefore, these two fields will add and will produce a total electric field along x plus direction at point A. Therefore, at point A, there will be electric field along positive x direction for the dipole. Okay. So for dipole, a dipole is shown here, positive and negative charges. One is Q plus, another one is Q minus. Surprising point is the distance between the two charges. Distance between the two charges is indicated as 2a but not a, 2a but not a, 2a. So point A is a point on the middle plane, mid plane of dipole. And at that point, the electric field is towards right, a horizontal line. Okay, actually the electric field lines are shown here. At point A, for these are not electric field vectors, these are electric line of force. For electric line of force, at any point electric field is along the tangent line at that point. Suppose this is a line, electric line of force. For this electric line of force, you identified a point A. At that point A, if you want to find electric field vector, you draw the tangent vector at that point. The tangent vector at that point will become like this. Therefore, electric field at point A is towards right direction. Okay. Now you consider here electric dipole is again shown here, a positive charge and a negative charge. Between them the distance is 2a. Here a new vector is shown, p bar. P bar is shown here. That p bar is a dipole moment unit vector. That is dipole moment unit vector. That unit vector is actually from negative charge to positive charge. Its magnitude is 1. And but direction is from negative charge to positive charge. And here also one point is selected, a point P along this is dipole axis. This is all dipole axis. On this dipole axis, a point P is shown. At point P, you will find electric field is towards left direction. At point P, there is electric field is towards left direction. Let us see why it is going to be towards left direction. All those things we will discuss in the next page. Here, but one point is p bar is indicated. P bar is a unit vector. A unit vector is shown, but because it is helpful for us, that unit vector is shown from negative charge to positive charge. And unit vector means its magnitude is 1. Okay. Actually, the letter P importance is there. The same letter P is used to denote unit vector and also dipole moment. Okay, dipole moment is a vector. The dipole moment is also indicated by letter P. The unit vector is also indicated by P. So we will have confusion. To avoid such confusion, we are using different notations here. P hat and P bar. P hat means unit vector along dipole axis. P bar means dipole moment vector. I am going to introduce dipole moment vector later, but you can conveniently understand unit vector along dipole axis because already it is introduced, but it is not yet introduced. But you have to remember that we are going to introduce P bar in the next coming pages. Dipole moment vector. Now consider the dipole. A positive charge, negative charge. This is dipole axis. Along the dipole axis, a unit vector is shown. A unit vector P hat is shown. P hat is from negative charge to positive charge. And also a between the positive and negative charge, a point is denoted as 0. And the distance from 0 to positive charge is A. Similarly, the distance from 0 to from point O to Q minus negative charge is A. So total distance from negative charge to positive charge is 2A. So along the dipole axis, a point P is shown here. At point P, the positive charge, this plus positive charge will produce electric field along this direction. Similarly, at point P, the negative charge will produce electric field along this direction. So the total electric field at this point is E positive minus EQ minus. Okay. Anyway, point P is at a distance of r meters from the center of the dipole. The point P is indicated to be at a distance of r meters. Whereas positive charge is at a distance of r minus a. Because we are measuring distances from 0 to point P. 0 to point P is r. So the distance from positive charge to P is r minus a. Similarly, the distance of negative charge, the distance from point P to negative charge is r plus a. Okay, this using this diagram, you can easily understand the distance between negative charge and point P is r plus a. The distance from positive charge and point P is r minus a. What is r? R is the distance from the center of the dipole to the point P. So electric field of EQ positive is at the EQ positive is the electric field of plus Q at point P. Point P is at distance of r minus a. So by Coulomb's law, electric field at point P is EQ plus is equal to Q by 4 pi epsilon naught r minus a whole square P hat. P hat means because E plus Q bar is along P bar. P hat. Okay, that is the way. Here this formula is written as K into Q by R minus A whole square, where K is equal to 1 by 4 pi epsilon naught. Similarly, EQ minus A is minus Q by 4 pi epsilon naught R plus A whole square P hat. Why it is minus? Because EQ minus is opposite to unit vector P hat. EQ minus is opposite to unit vector P minus. Okay, here I want to indicate clearly this one. Okay, this is what I want to include. I have included. Okay, right. P hat. That should be read as P hat. EQ plus is along the P hat direction, but EQ minus bar is along opposite to P hat. Therefore, we have included minus sign here. For EQ plus bar, plus sign is included. Total electric field at point P is EQ plus and EQ minus. That is what he here written. And after some manipulation, you will get 4QA by 4 pi epsilon naught R cubed P hat. P hat for R greater than A. Anyway, the numerator is 4QA, denominator is 4 pi epsilon naught R cubed. And the electric field is inversely proportional to R cubed. That is the important point here you have to notice. Electric field at points on the equatorial plane. Equatorial means between positive and negative charge, you will find a plane. On this plane, you are identifying a point P. At this point P, you are going to find electric field. The electric field already determined to be along the horizontal direction towards right. Okay, already shown in the earlier pages. Okay, here a dipole is shown. And okay, right. This is the okay, no problem. Okay, this is the point P lying on the equatorial plane. Okay, at this point P, this positive charge plus Q, this plus Q will produce electric field along this direction, along the line joining the P and positive charge. Similarly, at point P, this negative charge will produce electric field along the line joining, but towards negative charge. That is why EQ minus bar is shown here. Okay, for these two electric fields, we find a horizontal component and the vertical component. These vertical components will cancel together. And so total electric field is along this direction. That is what explained in the previously. And here this is right angle triangle. See that this is right angle triangle. This length is R, this length is A. Therefore, hypotenuse is root of R square plus A square. Similarly, this is right angle triangle. This length is A, this length is R. Therefore, this length is root of R square plus A square. Okay. Therefore, by using Coulomb's law, you can easily find that electric field EQ plus bar is Q by 4 pi epsilon naught 1 by R square plus A square. EQ minus is Q by 4 pi epsilon 1 by R square plus A square. But remember that here this electric field components will not add, but only horizontal components are adding, vertical components are cancelling. But horizontal components carry cos theta. Horizontal components carry cos theta. Therefore, EQ H bar, EQ H plus is equal to EQ cos theta minus Q by 4 pi epsilon naught 1 by R square plus Q square. And U minus QH is U minus Q cos theta minus Q by 4 pi epsilon 1 by R square plus S square cos square theta. Why minus signs are included? Why minus signs are included? Because between positive and negative charges there is a unit vector P hat. P hat is from right to left. P hat is from right to left. But horizontal components, if you find horizontal components are from left to right. These horizontal components are opposite to P hat. That is why we included minus sign for both horizontal components. And again from this diagram, cos theta can be found. See that if you consider this right angle triangle, cos theta is equal to adjacent side by hypotenuse. Hypotenuse is just now found to be root of a square plus r square, root of r square plus a square. Therefore, cos theta is equal to a by root of a square plus r square. Therefore, previous formulas are this one. EQ plus and EQ plus EQH is equal to EQ cos theta, EQ minus EQH is equal to minus EQ cos theta. In both cases, you are finding cos theta. Cos theta expression is now found. That cos theta expression is substituted here. Therefore, this is the formula. See that in the bottom, r square plus a square. Another factor is root of a square plus r square. So when you remove the square root, it becomes a square plus r square whole to the power of 1 by 2. 1 by 2 plus 1 is equal to 3 by 2. That is why you are getting EQ minus is equal to K minus KQ by A by R square plus A square into the power 3 by 2. Therefore, when you add all these things, total electric field is EQH and EQ minus H. If you add all those things, you are getting a final expression to be this one. On the equatorial plane, the electric field is 2QA P hat divided by 4 pi epsilon naught R cubed. This is what you are going to get. Of course, there will be minus sign will be there. I have not included here. Just I am going to include now. Okay. Okay. It is included. Okay, right. So, E bar at a point P on equatorial plane is 2QA 4 pi epsilon naught R cube. The product of numerator, 2QA P bar is called dipole moment vector. See that. The product 2QA P bar is called dipole moment vector. P bar is dipole moment vector. P hat is unit vector along dipole axis. The magnitude is 2QA. And 2Q means the distance between positive charge and negative charge. Okay. Q means either positive charge, magnitude of positive charge or the magnitude of negative charge. Okay, that is what. Therefore, the dipole moment vector is it is not cross product. It is Q small q multiplied by 2a. This is multiplication set. Don't think that it is a cross product. This is not cross product. This is a scalar multiplication symbol 2a multiplied by p hat. P hat is unit vector along dipole axis. P bar is dipole moment vector. So magnitude of the dipole moment vector is q into 2a is equal to q 2a. And torque, now later we are going to define torque for the dipole. The torque is equal to P bar cross E bar. P bar means dipole moment vector multiplied by electric field. That we discuss later. But remember that dipole moment vector is Q into 2A. Let us see what is its significance. If you place dipole in the electric field is positive charged plate, negatively charged plate. Between the two plates, electric field is there from positive plate to negative plate like this. In this electric field, if you place a dipole like this, okay, a dipole like this, what will happen? Okay, instead we take negative charge. Okay, like this. Okay, right. That negative charge will be attracted by positive charge, and positive charge will be attracted by negative charge. Therefore, there will be a rotating effect on the dipole. The dipole begins to rotate in clockwise direction about the point zero, about the point zero. So whenever the rotation is due to electric force of attraction between positive charge and positive plate and negative charge, and electric force of attraction between positive charge and negatively charged plate. Therefore, torque is equal to, we can derive the equation of torque to be P bar cross E bar. P bar means dipole moment vector. Dipole moment vector is P bar is equal to QA, P hat is equal to Q into 2A. So, this the magnitude of dipole moment. Magnitude of dipole moment can be written as charge of either charge of one charge. There are two charges in the dipole, positive charge and a negative charge. You can take either positive charge or negative charge in one in this bracket. The second term is 2A. 2A means the distance between the two charges. So dipole moment magnitude is one charge multiplied by distance between the charges. That is the significance. Let us see what is the significance of this dipole moment definition. Dipole moment magnitude is, I told you, 2QA, or charge one charge magnitude multiplied by distance between the two charges. Here two cases are shown. In one case, we have taken the dipole where positive charge is 2q, negative charge is minus 2q. The distance between them is 2a, only. For this case, you will find the dipole moment to be charge of one charge multiplied by distance between the two charges. Charge of one charge is 2q, but distance is a, but still the dipole moment is 2aq. Therefore, torque is equal to P bar cross E bar is equal to 2QA E bar sin theta. Magnitude will be same. But for the other case, in the second case, we have used another dipole. Each charge of dipole is carrying charge of only plus q and minus q. Compared to the first case, there are two charges in the first case also. One charge is 2q, another charge is minus 2q. But here only plus q and minus q. But here the distance between them is a, but here the distance between them is 2a. And if you calculate dipole moment, magnitude of dipole moment, charge of one charge multiplied by distance between two charges. Charge of one charge is 2q, but distance between the two plates, two charges is 2a. Again, you are getting 2aq. So here also the torque is same. What I want to say is, for both dipoles experience same torque, because the torque depends on dipole moment. The dipole moment is a product of charge of dipole multiplied by distance between the two charges. In that case, the two cases will produce same torque. Okay, another point is, once two charges are identified, positive and negative, along the dipole axis at one point, E bar is proportional to 1 by r cubed. But that is what? On the equatorial plane also, the E bar is inversely proportional to r cubed. So whenever you find electric field inversely proportional to r cubed, that case is corresponding to dipole, electric dipole. But here the point is one point. Here along the axis at some point, electric field is proportional to 2p by r cubed along the axis. But along the equatorial plane, electric field is proportional to p by r cubed. That is the difference. Okay, that is the difference. I explained in the classroom why such difference is arised. Thank you.